Is London dispersion. And first of all, before we get into London dispersion, and don't worry, I'm not going to talk in a British accent for it, we need to talk about why our molecules attracted to each other in the first place. And it's almost like you could think of it as gravity in some ways, but in this case, a lot of times there's going to be some sort of positive or negative, whether it be complete positive or negative, or even in nonpolar molecules, typically there's this temporary charge. If you remember right, that sort of slightly sigma, slightly negative or slightly positive that we talked about when we looked at polar molecules. So not only nonpolar or polar. So basically we're saying all molecules and atoms have this in between them. And the larger the charge, the stronger the attraction. So in the case of this, of course, this is going to be stronger up here, and this is going to be weaker in the attraction. And the longer the distance, the weaker. So that's, again, sort of like a little gravity idea here. The gravity that acts upon, say, like Mars is going to be a lot weaker than acts upon Mercury. So think of it that way, in the same way as atoms and molecules. And then it says, lastly, how are these attractive forces are small relative to the bonding forces between atoms? So it's hard to pick up on these always, but if they're kind of like tiebreakers. And so when we look at some examples, focus on those things. Let's see, what else do we have here? Oh, the trends. What are we looking at when we look at trends? So let's see here. We're talking about boiling. Why is boiling a good thing? Well, it's hard to actually look and see an atom and let alone see a force between two atoms. So since we can't see either one, we need to do something to make sure we can understand how those forces work. So one way we can do it is just boil it. So take the substance and boil it. And it says here, the higher the normal boiling point of the liquid, the stronger the intermolecular forces are. And a lot of times we just go ahead and we call this IMF, intermolecular forces. So that sort of makes sense. If it has a higher boiling point, it also has a very high intermolecular forces. So we're kind of looking at those and trying to figure it out through something like boiling. So the first one, again, is called London dispersion. And again, all molecules and atoms will have them, every one of them. And so with this, we're looking always to see, is there a distribution of some sort of dipole, and a dipole means some sort of positive or negative charge. Is this some sort of region that has that? And if it does, then that's going to make a bigger London dispersion. And again, sometimes it'll just be called dispersion forces, so you might catch on to that. Sometimes dispersion and London dispersions are the same thing, because every once in a while we kind of have these temporary dipoles. And it sometimes happens just because of which molecules are present. So if you look at this here, this kind of shows in some cases you'll have something, and I think all these are helium, if I remember. Oh, this one's helium. So we have helium atoms. I can tell it's helium because there's 2 protons right here. But even so, if you put all these helium atoms, now remember, helium is in the upper right-hand side of the periodic table. That means it's a noble gas. So what does that mean? Well, it means that it really doesn't have a charge, but even sometimes if you put, this is just showing there's sometimes dipoles that occur because of the locations of those molecules. And even though they don't have a dipole, an induced dipole can happen for just an instant. It's not very long, so this instant. And this is just a quick little attraction that can happen between the helium atoms. Maybe you have some in a balloon or something. The size of that depends on a lot of things, and it says the volume of the electron cloud. Well, remember, the volume of the electron cloud depends very much so on the how many electrons there are. Well, if you have a lot of electrons, that means you have a high molar mass, which means you have this huge cloud, and it's going to make a strong attraction. So the polarization, it's going to be able to make this attraction if you have a lot of electrons. Likewise, if it's a surface-to-surface contact, the larger the induced dipole can be. If we can kind of look at a few things here, for example, again, here's my boiling point. The higher the boiling point, that means the higher the IMF, because it's really tough to break it apart. So if we look at the molar mass, it goes down also. This is simply saying because xenon, krypton, argon, neon, as you go, has a huge electron cloud compared to a small electron cloud. As you get a bigger electron cloud, the boiling point gets larger. So as the boiling point gets larger, that means your IMF is also. Now, even though, like it says, noble gases are all nonpolar atomic elements, that's okay. It still has that dispersion forces because it has electrons, and so all that electron cloud can actually sort of kind of make an induced charge very, very transient, very short-lived. And it says the stronger the attractive forces between the molecules, like we said, the boiling point will also be higher. So this is the second point. If we're looking at electron cloud, we also have to talk about the molecular shape. Well, because of, again, if you look at N-pentane and neopentane, very similar in how many atoms there are of CH3. In fact, I think it's exactly the same. What you see here is there's this surface area right here, and because there's this surface area, we got a lot of opportunity for IMF. Over here, this area right here is a very small surface. So that's why when you look at this here, this one has a much higher boiling point over here, 36.1 versus 9.5 because of the increased surface. Number two, this is the second. So we had London dispersion was number one. The second one we're looking at here is dipole-dipole attractions. And the thing you want to remember on this is polar molecules have a permanent dipole, two poles, plus and minus on one location. And because of that bond polarity and the shape, the dipole moment will always exist, and that's pretty nice. So if we look at this, there's this slightly negative end, there's this slightly positive end, so there's this dipole-dipole attraction that's going to hold these two molecules together. And again, you raise the boiling point, melting point, it's going to be a lot higher than nonpolar molecules as long as they have a similar size and shape. So that's going to give us a high right there. Something cool to sort of focus on that takes us back is the idea of solubility. And solubility, remember, that's how you make a cloud, something cloudy. When you mix things together, that says it's soluble if it makes a cloud. So basically, those ions are breaking apart. And so when we remember this like dissolves like, we have polar molecules and nonpolar molecules. And this is sort of a side note, but polar substances are always going to dissolve polar solvents, and we call that hydrophilic. So we put any of these things into water, they're going to dissolve, but nonpolar molecules dissolve nonpolar solvents. So that's why it says like dissolves like, polar, polar, nonpolar, nonpolar. And all that means is it says many molecules have both hydrophilic and hydrophobic parts, and solubility becomes a competition. So if you look at this, this is called immiscible liquid, and what this means, if you would pour these two things together, water and this hydrocarbon right into here, pentane, then the pentane would actually float on the top, just sort of like salad dressing. Sometimes you see oil and vinegar, they don't mix, and that's what this means. A liquid that doesn't mix is called immiscible. Next up, we have polar solvents, and this just sort of shows that these polar solvents have these attractions right here, and those are dipole moments. And the polar solvents are always going to have that. Sorry, my circles went there with these green ones here, taking the electrons out, just like we talked last week. And I don't know why those are still there, but with polar solvents, no matter what the size, you have that. With nonpolar, however, you're looking at these and you're seeing that there's no real, even though there is a polar bond right here, overall this is a very nonpolar molecule, again, like we talked about last week. So sort of a side note on the polar and nonpolar, they don't mix. And because of that, solubility is very, very interesting. The third one, the third IMF, intermolecular force, is going to be our friend hydrogen bonding. And the reason I say our friend, because This is something that was definitely talked about a lot in biology last year. Hydrogen bonding is extremely important to life. And hydrogen bonding occurs when you have hydrogen, and obviously, and it bonds with FO or N. So remember, when a hydrogen bonding is very fond. So fluorine, oxygen, nitrogen are your, that's why it's so fond. Since hydrogen has no other electrons, just that one electron, it's just ready to lose that electron and exposes that proton. And that nucleus, it says, becomes deshielded, meaning that it's a very positive situation, H+, because that electron's been stripped off. And that proton acts like a very strong center of positive charge, and it attracts all the electron clouds from the neighboring ones. So, and because of oxygen, fluorine, and nitrogen being pretty electronegative, that works pretty well. And so when you look at this here, if you're looking at hydrogen and fluorine bonded together here, but more importantly, these charges right here make an attraction. It's called H bonding. And this is why water has so many kind of unpredictable properties that we'll talk about our next unit, or 2 units from now. Not too many units left, but talking about how the weird sort of the fact that ice floats because the water molecules become actually less dense when they're frozen. So anyway, H bond is very important, and again, it makes it so that water makes this nice, very predictable shape that can resemble a crystal. So when you look at a snowflake, if you ever had a snowflake land on you, like when you're wearing dark clothing, sometimes you can kind of see that really cool crystalline shape. It's because of these very rigid attractions that make ice look the way it does. Last but not least is the strongest, ion dipole attraction. And what that means is you typically have an ion like Cl or Na, and then a dipole, which means you have some sort of probably polar molecule. In this case, we have water. These water molecules right here. So because you have the ion, again, Cl or Na, and you have the water, which would be the dipole, you can have this sort of very, very strong attraction. So, and by the way, this is why, like when you put salt and you put salt into water, it can separate the water is very good at separating ionic compounds because of the ion dipole attraction. So here's a quick summary of what we're looking at, and as you can see, the first one we talked about was London dispersion models. Again, it's dispersion, London dispersion, same thing. You just know that all molecules and atoms have it. So no matter what, you're always going to have a dispersion, or excuse me, London dispersion force, and it's the weakest, as you can see over here on the right. Second, all polar molecules, if you have 2 polar molecules, they're going to display some sort of dipole-dipole IMF. And you can see it's sort of strong, but not really strong. Third, hydrogen. Again, hydrogen's bonded with one of the fonds there, FON, and that's the third. That's the second strongest, third weakest, and that is typically going to, a good example would be water, just like we have here. And then last but not least, the strongest is ion dipole. Typically, you're going to have a mix of ionic compounds and a mix of polar compounds. Usually think of water when you're talking about polar molecules, but it could be other things too. It doesn't have to be. So.